Okay everyone, we will start the class now. I hope everybody can see the slide. So we'll discuss about the types of shear failures of the soil first. Okay, then we'll solve the questions related to that. So coming to the types of shear failures of the soil, in 1973 Vesic he has classified the bearing capacity failures into three categories. So what is bearing capacity? See, let us take a footing. Okay, this is ground level or ground surface. So footing is nothing, it's a substructure, it's a part of the substructure of the building or any structure, so that will transfer the column load to the soil over a wide area. So suppose if you construct a column like this on the ground, it will punch, so it will fail. So you need a bigger area to transfer this load. That bigger area is footing here, that is called footing. So the footing, the strength of the soil for this footing size, the capacity of the soil for this footing size is called bearing capacity. Okay, see, bearing capacity is nothing but bearing capacity, generally it is from or due to soil. Okay, now there is a footing, this is footing, and this is column. Okay, so the load which is coming from the column is transferring to the soil through footing. Footing is now it is surface footing because it is just kept on the surface of the ground, so this is called surface footing. Suppose some embedded footings, other footings are called embedded footing, where suppose this is the ground level. Okay, then people excavate some soil, then they will construct the footing and column starts from that. So this is called depth of the foundation. Okay, this is called depth of the foundation up to the bottom of the footing from the ground surface. So this one is depth of footing. So this is, so then soil will be filled again after constructing here. So these are called embedded footing. Okay, embedded footings. So now, so there are another different shapes of the footing cross section. If you see from the top, footing can be square shape. Top means from here. Okay, so there is a column in between. Okay, column size is lesser than the footing size. If it is in the square shape, the cross section is, you can say like here at this level I am cutting. So if it is, or at this level, any level, if you can see from the top like this, if it is in square shape, that is square footing. Okay, and if it is rectangular shape, rectangular. Okay, and circular. Sometimes footing, I'll show you it roughly. I'll draw a 3D diagram. Okay, this is ground level, suppose. Sometimes footing this is column. Okay, so like that there are number of columns. Sorry, suppose another column is here. another column is here like this. So for all columns, if you go for the same footing is same, okay, it is very long, the width is, compared to the width, the length is very much higher, okay, L is greater than B, okay. I hope you can understand. This is ground level, so this is the depth of footing, okay. So this is footing, this is there up to just, it is continuous footing. These are called strip footing, okay. There are another different kinds of footings anyway, so we'll discuss whenever it is required. Now these footings will have some capacity to take the load from the structure, so that capacity is dependent upon that capacity. That capacity is from the soil should not fail. So that is what the capacity, the capacity or the strength at failure is capacity, okay. Just before failure, whatever is the strength or stress at failure, stress at failure, not strength at failure, stress at failure is capacity. Whatever is there, pressure which soil can take is the bearing capacity. That depends upon the size of the footing always. If you take bigger size, the capacity will be more. If you take smaller size, capacity will be more. So capacity of the soil, that is bearing capacity of the soil, will depend upon the dimensions of the footing, okay. You cannot say soil has some capacity without having footing dimensions. So it is both the ways you need to consider the soil parameters as well as the footing size. So that is what about the bearing capacity. Now I hope everybody can listen my is it audible? Can somebody reply? And can you see the slide? Can anyone reply? Yeah, okay. So let us enter into types of shear failures. See, another thing is soil fails only in shear. I already told in the previous classes. See, this shear will happen due to the sliding of the soil particles one over another. There are soil particles, some soil particle move in this direction, some soil particle move in this direction. So like that, because of the failure in the shear, the soil will fail, total soil will fail. Suppose you take ground, suppose there is a footing. Now because of the footing may go down or may rotate, suppose it is rotating. Why? Because soil has gone down, so it failed, it cannot take any more load. The failure can only happen in shear. Now what are we discussing here? Now we will discuss about the types of shear failure, okay. Basic in 1973 he has classified the bearing capacity failures. Bearing capacity shortcut I will write BC. Capacity bearing capacity failure, bearing capacity failures he classified into 3 categories, okay. So first one is general shear failure, okay. All are shear failures, but there are 3 categories in those shear failures. First one is general shear failure. So first I'll draw a diagram, okay. I'll go to next slide. general shear failure. Okay, let me draw diagram first. Suppose this is ground level and let us take it some depth. Okay, now due to the load which is coming from the column, now if you draw the corresponding load versus settlement diagram, okay, if you draw, let us say this is bearing capacity or stress, this is load per unit area. Okay, suppose this is, we'll take a strip footing. Suppose if you see from the front strip footing, you can see this width B and height H. Okay, that is what I am drawing here, width B, height H, and this is DF. Okay, I am not considering any length here. Let's take strip footing, and the load per unit area, you can take 1 meter length and you can calculate load per unit area, that is Q. Okay, for some Q there will be some settlement is, okay, S, denoted by S. Now whenever you apply, whenever you start loading it, what happens, let us, general shear failure can happen in dense sand, and stiff clays. Okay, now here this, the response of the footing whenever you apply load in this dense sand or stiff clays, the load settlement curve will be somehow, it will be like this. Okay, this is ultimate pressure. Now at certain load intensity like this QU equal to QU, that settlement will, what will happen to the settlement suddenly will increase, okay, without taking any further load. Instead, in fact, the load carrying capacity will decrease after this point. Slowly, whenever you are applying load, the load will increase, it can take further load, and settlement will also increasing. Then at certain point, what will happen, the settlement will increase suddenly without taking any further load. Okay, in that way shear failure happens in dense sand and stiff clays. The settlement, load settlement curve will be looking like this, and let me erase this B, and the failure surfaces, how do they occur under the footing, I will show you now. They will occur like this. Okay, there will be different zones formed. This is ground level anyway. See, these are different zones. This is elastic zone, and this is radial shear zone, and this is passive zone. So depending upon the response of the soil wedge, these are called wedges. This part will be at the failure of the footing, this part will be in the elastic zone only. Elastic that response is under elastic only. Then what will happen, this is the zone which will be subjected to the shear, that too radially, it will move in radial direction, whereas this will be pushed up. So that is the reason why this is called passive zone. There are different zones are formed. Then at the failure, at this QU, there will be eaves formed sides of the footing. Okay, heaves matlab the soil gets lifted up at this portion. So whenever you are trying to fail the footing, whenever you are trying to apply the load on the footing in this dense sand and stiff clays, what happens, the failure surfaces, these are called failure surfaces. This is failure surface. Okay, this is also failure surface. These surfaces will reach the ground. This is ground, it will reach the ground. Then there will be heaves, these are heaves, lifting of soil. It will happen sides of the footing. This is called general shear failure, and general shear failure happens in the dense sand and stiff clays. And the load settlement graph or response will be like this. So we'll talk about another second kind of shear failure, that is local shear failure. Okay, that is local shear failure, second one. Second one is also, let us draw the footing again. Okay, you know this is ground level, and here also wedges will form when you apply the load. Okay, now here load settlement graph will be Q, and this is settlement. Now whenever you apply this, local shear failure happens in the medium dense sand or clays with medium consistency. Okay, now seeing the we'll see the load settlement graph. Whenever you apply load, it slowly increases. Okay, at one point of loading, let us say QU1, at one point of the loading, sudden jerk will happen. Okay, in the footing with small jerks. It slowly tries to take some more load with some jerks. The settlement will slowly will increase compared to this. So with small jerks it will increase. Then after certain point of loading again, okay, let us say this is QU, then the settlement will increase rapidly. Okay, with again jerks. So because here this is medium dense and clays, because of that what happens, this failure, these are the failure surfaces. Okay, whenever this failure surface is within the footing area up to here, it will go up to QU1. Whenever it is crossing this particular point with sudden jerks, settlement will increase. So then slowly the failure surface tries to reach the ground surface. After reaching that, suddenly the settlement will increase suddenly. Okay, a small heaves may be observed here also. A small heaves may be observed. Okay, so that is how local shear failure happens. And third one is, punching shear failure. Punching shear failure. So in the punching shear failure again we'll go for load settlement graph. I'll take here also with large settlements. Again you will observe at one particular point again jerks will start here also, then after that again it will become more steeper after certain point QU. So this is Q, this is settlement. So here in this it will happen in loose sands or clays with low consistency, or you can say soft clays. In that what happens, only failure surface will not extend to the ground surface because it is very loose. Because of that this footing gets punched. It can be punched to the lower depths where the soil is here, let us say. The failure will happen before reaching the failure surface to the top. So it has very less strength. So there will not be any failure surfaces here. No failure surfaces. That is called punching shear failure. Now you can observe whenever going to any dense sand or stiff clays, when you put your leg, when you punch with your leg, what will happen? Suppose this is ground. So this is just ground. When you put your leg here, what happens? Sides of the footing, sides of our foot, it will heave will form. But when you put in the loose sand, your leg goes inside, your foot goes inside, but there will not be any change here, any heave or anything. So it is nothing but you are punching because of the loose sand. So now what did you understand from this? General shear failure can happen in dense or stiff clays, dense sand or stiff clays, and local shear failure will happen in medium dense, okay, or medium consistency soils, and punching shear failure will happen in loose sands. So in dense sand, what is there? The packing will be more between the grains. Intergranular packing will be very high in the dense sand. In the medium it is a little less, and in the loose sand it is even less. Soft clay you can write here. So now this is all about the shear failures and different types of shear failure which exist. Okay, now let us go for question. So it is in 2011 GATE paper. It is question number 11 and 1 mark question it is. So the question is about likelihood of general shear failure for an isolated footing in sand decreases with. Let me go through again. See, likelihood of general shear failure for an isolated footing in sand decreases with. So what is it? The likelihood of means the probability of general shear failure in sand decreases with, means you should not have general shear failure. That is the meaning of this. So that is what, right? Likelihood means probability of GSF in sand. When does it, when will it be low? When will it be decreasing? When will it be low? Decreasing footing depth. So if you decrease the footing depth, okay, this is the footing depth. If you decrease the footing depth, so what will general shear failure will happen, because the failure surfaces will reach ground surface. So this is wrong, because by decreasing the footing width, increasing of general shear failure will happen. General shear failure will not decrease with the decreasing of footing. Decreasing intergranular packing of the sand. What is it? Decreasing the intergranular packing. So what is it saying? That footing is there. So when you are decreasing the intergranular packing, means you are loosening the soil, right? You are decreasing the intergranular packing, you are decreasing the packing. That means what? You are actually loosening the soil. When you are loosening the soil, what will happen? Punching shear failure will happen. So the likelihood of GSF will decrease. So this can be right. So increasing the footing width, if you are increasing the footing width, How does it related to the general? It can reach the ground surface easily. And decreasing the soil grain compressibility. When you are decreasing the soil grain compressibility, that means what? The compressibility of the soil is decreasing. That means it is stiff, it is dense. It is dense. When it is dense, general shear failure will happen. When you increase the footing width, when you decrease the footing depth, every time general shear failure will happen. But only when you decrease the intergranular packing, when you loosen the soil, then only this likelihood of general shear failure will decrease. So option B is correct. Coming to this question, depending upon the discussion which we had just now. Okay, any doubts in it? Is it okay? Can I continue with the next question? I hope it is okay, because you are not responding. Is it fine? Okay. Okay. So I am shifting to next question. So this question is from GATE 2011 paper only. Again, this question is 12th question, which is of 1 mark. Okay. So let us go through this question. For a sample of dry cohesionless soil with friction angle phi, the failure plane will be inclined to the major principal plane by an angle equal to how much? So this is again related to the Mohr circle. Okay, Mohr circle. I hope you are very comfortable with Mohr circle right now, as per the discussion which we had. So given data, cohesionless. Okay, cohesionless soil, that means cohesion will be 0 and phi is given. Phi, it is denoted by phi. It is not equal to 0. Here, whenever you take some soil sample of cohesionless soil, the failure plane, whenever you apply load, the failure plane will be inclined to the major principal plane by an angle equal to. You should find out the angle between failure plane and major principal plane. So this is what. So let us draw a rough Mohr circle. Sorry. So as it is, as C is 0, as phi not equal to 0, cohesionless soil, so there should not be any intercept, Mohr Coulomb failure envelope. So I can draw one line like this, right? See, Mohr Coulomb failure envelope equation is what? Shear strength. This is tau, this is sigma, or nothing but shear strength. Shear strength is equal to C plus sigma tan phi. This is normal stress, this is cohesion, this is friction angle phi. If this is 0, it should pass through the origin, and here this equation become tan phi. Okay, this is nothing but y equal to m x. M is nothing but slope, where tan theta, phi equal to angle of inclination of the this failure envelope. This is the failure envelope. Okay. Now what do I do? So I am drawing a Mohr circle. Okay. This is sigma 3. This is sigma 1. This is major principal stress. This is minor principal stress. Okay, so now let us take a element. Let us take an element. Just give directions of the major principal stress and minor principal. You just give any direction. Okay, you can give this sigma 3, sigma 1, or you can give here sigma 3, here sigma 1, no issues. So this is sigma 3, this is sigma 1. Okay, now according to this element, okay, we will find out where is the pole. Okay, according to this directions of the stresses, we will draw the pole. So now how to draw the pole? We just have to draw the lines parallel to this planes. Okay, where is sigma 3 acting? Sigma 3 is acting on vertical plane, right? So I will draw a vertical line through sigma 3. So I am drawing vertical plane. And where is sigma 1 is acting? Sigma 1 is acting on horizontal plane. So I will draw a horizontal line from sigma 1. Okay, I am drawing. Wherever these two lines coinciding, that is called pole. This is pole, denoted by P, let us say. Now pole is used to what? It is used to find out the inclination of the any plane. So suppose I want the plane, inclination of the plane on which this much sigma is acting and this much tau is acting, let us say. This much tau, this much sigma. So this is the plane. Some, let us say sigma I comma tau I. Okay, so the plane on which this much normal stress, this much tau is happening, subjected. So what is the inclination of that plane? So you just have to join this pole and that point, that's it. So this is the angle of inclination of the plane with horizontal. This is the alpha I. That is how you just find out. Now if you know the failure point on this circle, if you know the failure point, you will just join the pole and that point, that's it. So what do I do? Here I will just erase this. Okay, so where is the failure point here? Color, there is no color. I will go with this is the failure point. Why it is failure point? Because this is the intersection between the Mohr Coulomb failure envelope and one point will touch. This is the failure point. Okay, this is called F, let us say. So if you join this pole and the failure point, this is the inclination with respect to what? So if you draw vertical line, with vertical line this much angle, with horizontal line this much angle, but we need what? The angle between failure plane. Failure plane we found out. What is the major principal plane? This is the failure plane, that we understood. What is the major principal plane? You just have to connect major principal stress and pole. So that is nothing but horizontal line here. So I am drawing from pole to sigma 1. This is another plane. Okay, this is the plane, major principal plane, and this is the failure plane. So you need to find out the angle, this angle, that is the thing which is asked. So how to find out this? Let us join center. Okay, you know this angle, actually I couldn't draw nicely, but anyway, so I'll take failure point somewhere here. This is failure point, let us say. This is the failure plane. Okay, so now you need to find out this alpha. So this is failure plane, this is major principal plane. We know this angle is 90. This angle is 90. Why? Because you are connecting point of intersection of the tangent and the circle, this point, to the center of the circle. So it will make 90 degrees with the tangent, that we know according to the properties. Now, so this already I derived in the previous class, right? You need to find out alpha, that's it. Now in this big triangle OCF, in OCF, if this is phi and if this is 90, this should be 90 minus phi, right? Total, so that total will be 180. Now, so you know this angle. Now I'll consider this P. This is P, right? This one is P. Now let us go to the triangle PCF. PCF. In PCF, there are two angles, alpha, and this angle will be there. Let us say this is alpha 1, this is alpha 2, and there is another angle 90 minus phi. But here, according to the triangle properties, alpha 1 and alpha 2 are equal to each other. Why? See, from P to C, PC is nothing but radius. PC is nothing but radius, whereas PF is also radius. The angles opposite to equal sides will be equal. So alpha 1 and alpha 2 are opposite to the equal sides. So alpha 1 equal to alpha 2. Now in this triangle PCF, so alpha 1 plus alpha 2 plus 90 minus phi equal to 180. Okay, alpha 1 plus alpha 2 plus 90 minus phi equal to 180. Then alpha 1 alpha 2 both are equal. Let us say this is alpha, this is also alpha. 2 alpha plus 90 minus phi equal to 180. Then what is alpha? 180 minus 90 plus alpha divided by 2. Alpha equal to 90 plus phi by 2. Alpha equal to 45. This is the angle. So let us see the options. Phi 45 minus 5 by 2. So this is the answer, right? This is the answer, 45 plus phi by 2. So is it okay? Shall we move to another question? Okay, I hope it is. One minute. Okay, so I am moving to another question. With this question I will end this session. Okay, so this is also from the same 2011 paper. So question number 37 of 2 marks. Okay, this is regarding the consolidation topic. So in the consolidation topic, so I have already discussed consolidation. I have already discussed the one-dimensional consolidation equation. After solving that, we have got 2-3 different parameters. One of them is CV, TV, coefficient of consolidation, and this is time factor, and the TV is CVT by D square, where D is drainage path, T is time, some particular time, CV, you know, this is constant for a soil, okay, for a particular soil. So now let us consider, this is clay, let us say. Now whenever you are applying load, this is the ground level, this may be sand, let us say this may be rock, you are applying load. What will happen? Clay gets compressed. Whenever clay is getting compressed, the water which is inside the clay, that has to travel. It cannot enter into the rock because this is impervious, okay, this is impervious. It should go to only sand because sand is pervious. So the water whichever is at this point, that should travel this direction. Whichever is here, that also will travel this direction. The maximum path taken by a water particle in the clay is drainage path, equal to D, okay. So and it is happening, drainage is happening only in one direction, because only sand is only there only in one direction. That is the reason why the drainage path is equal to height of the clay completely. Let us say this is H. If there are sand above and below, this is clay, what will happen? Water will go here, it can go from this direction also. So maximum path can be traveled by this half of the height, so H by 2, D will be H by 2 in this double drainage case. This is single drainage case, okay. So you understood the drainage path actually in the previous classes only. I am just repeating the same thing. So we need this now. This is the drainage path, this is the time taken for the consolidation, any consolidation, 25% of consolidation, 50% consolidation, whatever. So this is the coefficient of consolidation which is constant, okay. This is the discussion about the consolidation. So let's see what is it said in this question. So identical surcharges, see there is some surcharge on this, so this is some surcharge on two different sides, both are identical, okay, means they are equal to each other, placed at ground surface at site X, this is site X, this is site Y, with soil conditions shown alongside and water table at the ground surface. See, water table is at the ground surface, okay. Now the silty clay layers, see this is the silty clay layer, this one is the silty clay layer, this is also silty clay layer. At X and they are also identical. The thin sand layer at Y is continuous and free draining with very large discharge capacity. See, in the site Y, there is one thin sand layer is existing in between the at the middle of the this saturated silty clay. It is just this is present. That's it compared to X. Now, if primary consolidation means it means the consolidation which happens due to expulsion of water. See, consolidation can happen due to the elastic settlement of the clay, and it can happen due to water is expelling out, and other reason is the disintegration of the particles. So when the particle is crushed, because of that also soil can settle, consolidation can happen. But the primary consolidation means it is due to just there is any there is no disturbance in the soil grain, but there will be expulsion of the water. Because of that, the volume gets reduced. That is called primary consolidation. So here he did not mention any percentage. That means complete primary consolidation, complete 100% consolidation is at X is estimated to complete 36 months. It will take 36 months at X. Okay, you can say Tx 36 months for the consolidation. What would be the corresponding time for the completion of the primary consolidation for the same consolidation? Means same percentage of the consolidation at Y. Okay, at Y, how many months? Okay, how many months it will take? See, let us at X side, okay, the height is 10 meter. At Y side also 10 meter. This 10 meter only total, but at middle there is some thin sand layer is there. That's it. Okay, this is Y side. Now here what is given? Bedrock. There is nothing above ground level, right? So this is bedrock. This is also bedrock. That means impervious. Water cannot percolate this direction. It cannot happen. Here also it cannot happen. Only water should travel in this direction. Okay. So what is the drainage path in this X case? What is dx? Can somebody tell me? Ten, right? So sand is at the middle. Okay, 5 meter in this Y. Can somebody tell me what is drainage path in this? See, water can go here, of course, in the sand, and water can go up, and here water can go only to the sand layer. Okay, it cannot go down. Okay, now tell me what is the dy? How 5 meter? Can you tell me? Yeah. See, suppose in this upper part, if you take any particle, in this it will travel only 2.5 meters, because it can go up, it can go down, only 2.5 meter. But in this part, the farthest will be at distance of 5. So you have to take 5 meter, right? The farthest distance traveled by any particle, this is 5 meter. So dy is 5 meter. Here dx is 10 meter. Okay. Now primary consolidation is 100%. Whenever consolidation u is constant for both, that means tv is nothing but what? Pi by 4 u by 100 in percentage whole square if it is less than 60%. If u is greater than 60%, I have given the empirical formula. Anyway, if u is constant in both, tv is also constant for the both sides. See, anyway, for both sides you have to calculate complete primary consolidation. That means tv is same. So tv is same. dx and dy are different, and we need to find out what is tx, ty. Tx we know 36 months. What is ty? And also cv is same, because same clay is undergoing consolidation. tv equal to cvt by d square. This is the formula. So this is constant, this is constant for both. Now t equal to tv d square by cv. That if this is constant for both soils, t proportional to d square, ty by tx equal to dy by dx whole square, right? So ty, what is tx? 36 months. What is dy? 5 meter. What is dx? 10 meter. 5 2s 36 by 4, 9 months. Okay, ty, this site y will take only 9 months compared to this site x, 10 here 36 months. Why it takes less time? See the calculation. Ty equal to tx into dy by dx. Dy is 5 months, sorry, dy is 5 meter, d10 is 10 meter. So after calculating you got ty is 9. So as this is in months, this is also in months, 9. So it is lesser than the 36, means x site. Why? Can somebody tell me why it is? Okay, see, whenever it has to travel less distance, water, to consolidate, it will take less time. That's it, it's common sense. So 9 months, C is the correct answer. Okay, so I hope it is cleared. So these are the 3 questions for this week. Any doubts? Shall I end the session? Can somebody tell me? Can I end the session? Yeah. Okay. Bye guys. So we'll meet in the next class.